Afternoon, everyone, and welcome to the School of Computer Science and Mathematics at Liverpool John Moores University, where we've got a series of three really interesting tech talks for you this afternoon. And just as a way of introduction, I think it's an extremely exciting time to be involved in computer science for a wide variety of reasons. And that computer science is being applied to lots of areas that are of concern to all of us, such as biodiversity, climate change. And of course, the other side of that is we need to protect ourselves from becoming more digitally immersed. And so we've got talks today on cybersecurity. We've got a really interesting talk on the application of machine learning, which I'm sure many of you have heard about this afternoon in its application to conservation and biodiversity. And we're going to start with a really interesting talk from a senior lecturer in the school on our computer games development course, Dr. Chris Carter. And he's going to talk to you about Unreal Engine, which is being used extensively now, not just within the games industry, but within film and TV production and many other areas, and is becoming an increasingly important product. So without further ado, I'll introduce you to Chris.
Afternoon, everyone. I hope you can hear me clearly. Welcome to today's talk on computer games development. The focus of my talk is what makes a $29 billion game engine. So what I'll try and do is show you some live demonstrations. We'll be doing that directly from a camera feed. So I will stop sharing the slides at any point. I will post in the chat just to make sure that you can see the screens okay. So I'll just pan around to the screen now just to make sure it's in view. And then we'll make that full screen when we do the demonstrations. Okay, so what makes a game engine worth $29 billion? That's the question that we're trying to answer in this talk. The engine in question is Epic Games' Unreal Engine. It is the industry-leading game engine in the game industry sector and has been developed over 30 years to become this dominant product. Its valuation is quite complicated. They have one big hit, which is the game Fortnite, which I'm sure many of you have played many times, which has become such a commercial success that drove the rest of the business. But that is not the reason why Epic is worth this value. That reason is actually the game engine itself. So therefore, I'm going to try and explain to you what's inside a game engine, demonstrate how we can apply it to all these different domains. As Atif mentioned, we can move into not just games, but film, TV, augmented reality, virtual reality. So hopefully I'll give you a demonstration of some of these techniques and how they're used across this talk. Before we get into that, the first thing that we need to look at is putting it in context just how big the games industry is. We term this AAA development. AAA refers to those games that you can buy off the shelf for your Xbox Series X or your PlayStation 5. And at the close of last year, the games industry had a value of $159 billion. If we take a product that was developed in the UK, Rockstar's Grand Theft Auto 5 sold 175 million copies within its history. Games nowadays have enormous budgets. So 170 million was invested over 5 years to develop that game, but it paid off. Within the first 24 hours of the game being released, it generated nearly £500 million worth of revenue across 11 million copies of that game. Okay, just to give you a sense of the scope of the games industry. Their follow-up to that game, Red Dead Redemption 2, was estimated. Now, we haven't got a concrete figure on this, but certainly from the accountant's audits, it cost $300 million to develop. And that cost really is down to the human manpower that's needed to actually develop these types of applications. So nearly 2,000 developers over a 7-year period were involved in the production of that game. Now that means that the games industry is somewhere where there's a lot of elite programmers, people working with extremely complicated tasked across the artistic realm and the programming realm in order to build this kind of software. And underpinning all of this is this concept of a game engine. So that's what we'll focus on today. Meanwhile, esports has become a lot more popular. Gaming culture has kind of taken over, where it's no longer just a niche pastime, it is just a mainstream activity now. And because of that, gaming has become a lot more competitive. And because of that, players can net enormously large sums of money from playing games. So a lot of media coverage is centered around this. If we have a look at this Guardian article from 18 months ago, it was lauded of this 15-year-old boy winning close to £2 million playing Fortnite, proving that putting your time and energy into playing games is not a waste of time. Now, as someone who teaches games development, I'm certainly not going to argue that playing games isn't a great activity. It definitely is becoming a more competitive realm. But what interests me as an academic much more is the actual production of these kind of tools and techniques. So this boy in the right-hand corner with the I Love Pac-Man t-shirt, who spent his time as a child growing up, messing around with engineering projects, learning to program, is the person who is behind the Unreal Engine. And his name is Tim Sweeney. Tim Sweeney owns roughly half of Epic Games and has just netted this $29 billion valuation. So while the 1.5 million might be netted from playing games, if you can get elite in your field like Tim Sweeney, then you can grow your wealth to $14.5 billion instead. So obviously quite a big difference there. Fortnite is so big because of its user base. Over 350 million people have played it since the last 4 years it was released. And that, just to put it in context, is more players than the PlayStation 4 and Switch combined. At the moment, they're currently embroiled in a legal battle with Apple, trying to get Fortnite back into a system where they'll be earning the revenue directly from selling it on iPhones. Apple obviously want to keep their cut of that. So that's currently working its way through the courts. But prior to that, there were 6 million monthly mobile downloads for Fortnite. So it's not just on the consoles and PC. Mobile gaming has also taken off. Their revenue for last year was 5.1 billion. And a lot of that comes not just from the game itself, but from the actual engine technology. It's simply the fact that Unreal is so powerful and can be used in so many different contexts that it's allowed to grow it to this enormous size. So what actually goes into building a game engine like Unreal? Well, Unreal is comprised of lots of different components, and we can break those components apart based on their function in the game. So we have audio engines to power the audio side, a rendering engine, which is what powers the 3D graphics. And at that point, what we've got is a great looking visual representation, but we've not got a game. So to actually turn these into applications where you have an interaction with that virtual world, we have to combine physics, input, and artificial intelligence into that to then become a game. So it takes it beyond the graphical demonstration into a working, living, breathing piece of software. And this is what we mean by a game engine. A game engine is simply a collection of the programming code to represent each of these major domains. So we have 3D graphics, physics, animation nowadays is driven by what we call skeletal animation, which I'll give you a demonstration of in a second, virtual effect systems, linear algebra, so a lot of mathematics, and I'll again demonstrate that to you in a couple of seconds time. But we're also working on all these different unique tool sets. So things like the PlayStation 5, all the way through to headsets like Microsoft's HoloLens 2, which is a mixed reality device or an extended reality device, one that does both augmented and virtual reality. I'm afraid there's a lot of buzzwords in the games industry, so I'll try and show you demonstrations of exactly what we mean by each of these technologies. But I'm sure you've encountered VR and AR before. So Therefore, we can define a game engine as a piece of software split into different libraries of code or areas of code that take care of the majority of the work in each of these areas. And Unreal has close to 7 million lines of this code that we get to utilize to then build our applications. Unreal is about to release a new version, Unreal Engine 5, which I'll demonstrate right at the end of today's session to show you just how powerful these modern platforms are. But we'll start by looking at the current version of the engine, which is Unreal Engine 4. So what makes an actual game application? Well, games are a mix of the graphical side. So when we're building a game, we're building terrains, water systems. We're trying to represent the reality of life. So therefore we have atmosphere systems that model the stars, model clouds, model the color of sunlight. We have all these different graphical effects that try and trick you into believing that the image that you're getting on your TV screen is as close to realism as possible. But aside from that, we then have the actual behavior or the code that makes up the game. So that's things like weapons, enemies, vehicles, characters, non-playing characters that are driven by artificial intelligence, and the puzzles and challenges that you have in making a game. Everything beneath this level is the job of a game engine. So a game engine allows us to just focus on building the game itself and building those mechanics into place. Now, what we've seen is that there's a big share between these applications and other areas of development like virtual reality and augmented reality. So if we extend this concept of a game engine to not just being games nowadays, but actually any interactive 3D application, then all of a sudden there's another realm of applications that we can build using these technologies. So this image of the layers of a virtual reality system, you can see very, very similar to a game. Now we're dealing with the actual virtual reality headset. We're dealing with tracking someone's hands, tracking where the motion controllers are, tracking aspects that we can interact with in virtual reality, and also draw to these virtual reality headsets. And we use the same techniques that we use to draw to a standard television on your console games. We're simply drawing it twice, once to the left eye, once to the right eye, in order to trick your brain into believing that this is one complete world that we're representing. To do that, we've also got a set of programming languages that we can work with to build our code. And this will be the first demonstration that we look at. Broadly, we can define a game as a mixture of the artistic elements created by the 3D modelers and the animators. So that's our 3D models that represent all the geometry in our world. And then we have our code and script representing the behavior of the game. And these two aspects combined give us our gameplay and mechanics. So we'll jump straight in with a live demonstration of some simple gameplay concepts. Okay, so hopefully you can see my screen relatively clearly. So we'll just load up an Unreal application. So we'll start with a demonstration in Unreal's inbuilt language, which is known as blueprints. Blueprints are there to make it easy to represent game logic in a way where we don't need to be a fully fledged programmer. So we're trying to allow people who are not traditionally programmers, people who may be artists, people who may be the people who design the levels of a game, the ability to actually implement game code into their game application. So what we've got here is an Unreal world, and I've just built a simple demonstration. You can see that with our world is just this very simple level made out of a few blocks. Now, the first thing that I want to get across to you is the fact that this world is actually all just comprised of thousands of individual triangles that are connected together. So that's where the mathematics comes into place with games. We need to know all about how triangles work, how they join together, how we can move triangles around in our world. So I can take this object and I can move it about. And this relates to, I'm afraid, the stuff that you looked at high school, where we look at graphs and we draw squares on a graph and move them around, translation, rotation and scale. the stuff that many people say they'll never do again once they leave school. I'm afraid as game developers, we do this every single day of our lives. Lots and lots of geometry that we have to deal with. So at this point, what we've got is just a graphical demonstration. And if I put our world back again, sorry, wrong mouse, put it back to our normal view, what we can then do inside the engine itself is actually launch the game. And you can see what we've got is a character that's been driven by my mouse, which I can now move about in my world. Now that movement is all created by translating and moving the objects around. So I'm shifting all of those triangles together, those triangles that make up the character's view, and move to left and right. And then what we have is the elements that are static within our world. To actually build it into a game, we then have code which drives certain parts of the game. So in this example here, what I've got is one mechanic where if I walk up to an object and fire at it, you can see that it will destroy the objects and remove them from the world. And that's what we're aiming to do when we build a game. Just put these simple mechanics in place and hopefully allow us to build rules of a game into place. And you can see that all the objects that I'm firing are being simulated under real world physics. We can see the objects bouncing. Now, that's not scripted. That's not hard coded to do that. That's just simply implementing Newton's laws of physics to go and drive this. Okay, so we call this emergent behavior, and that is what's built into the game engine. Epic Games have written a library which allows us to model things under Newtonian physics to go and interact. So if we take that, an example of that script code, we'll just have a look at a different example. Now, this is an example that I built for my 6-year-old son, and we're currently working on together. This is my way of teaching him healthy eating. So over time, we have the ability to drop fruit into the world. Our character is getting hungry, losing energy. So if he eats something healthy like an apple and collects those fruit, then he gains energy. And if he eats enough healthy stuff within a day, hopefully he can then get through the rest of the day and complete the game. Now, this is a very simple demonstration, and you can see that I've won the game. That's a very simple demonstration, but it does get across the concept of a full game. Scaling this up to a game like Fortnite is simply designing the mechanics and then implementing the code behind them. So let's just stop the game and have a look at a little piece of that code just so we can demonstrate what goes behind the game engine. So this is Blueprints. Blueprints is a visual programming language. So it's not typing out characters like we would with a traditional program language, but rather giving this ability to wire concepts together. Now, I'm afraid in a 40-minute session, I can't teach you everything that goes into Blueprints, but what broadly we've got here is events that handle input. So in this case, when I press the key to turn the character, what I'm doing is working out what rate do I want to turn that character per second, and then I apply that to a rotational part of the character. And yawing means I'm twisting the character left and right. So that's basically how I steer my character. How do I work out where those bits of fruit are? What I have is a giant sphere around the character. Okay, and you should be able to see a capsule there as well. And I use that to work out whether I'm overlapping with those pieces of fruit. So at that point I'm overlapping, I can then write some code to actually go and collect that fruit. And in that case, it will then award energy to the player. So what we're really doing here is algebra. We're implementing algebra into our code. Okay, so let's extend that concept to a different domain. Rather than being a game, let's see how those concepts apply to virtual reality. So I'm going to pop on my virtual reality headset and just make sure it's all connected up. Now, Unreal Engine supports devices like this one on my head now, which is the Oculus Quest 2. There's many virtual reality headsets coming out there. In this case, I've connected it directly to my PC. This one can actually be existing without a cable connected to it. But in this demonstration, we'll do it directly from the PC. So we'll use Unreal again. And load up our scene. And this time we're going to play it directly on the virtual reality headset. So hopefully you should be able to view what I can see. Now, those same rules of physics are going to be used in our virtual reality application. In this case, I've got the ability to create a parabola, this nice curve, which is going to define exactly where I'm going to locate my objects. Those same overlap concepts to pick up the fruit apply to these objects, but because I'm in virtual reality, the interactions are much smoother. You can see these two blue spheres, hopefully. That's my hand tracking. So it's tracking exactly where my hands are positioned and how the objects move around. So that means that I can touch this lever, drop these objects to the floor, and then I've written this piece of code which allows me to pick up these objects. I can chuck them, and I'm afraid I can't catch very well, and build interactions. Those same interactions, just by changing the code, I can move them to do things like opening a door, or I can implement being able to pull a drawer out, all in these virtuality spaces. If I'm really smart with it, I can even do things like build it where I can actually write my own name in virtuality. And that's that additional layer of virtuality that really is bringing Unreal to the forefront. It's such a powerful tool. The concept's exactly the same as what we use in games, but allow us to extend into this, this new dimension. So our job of a game editor is basically allowing us to position stuff inside a virtual world and then build that to start building up these applications. Now, how we can support this technology is by increasing the power of our hardware. That machine that I'm running these demonstrations on is a £4,000 PC, and I'm afraid it has to be that powerful to support all of the concepts that we use. It can be cheaper when you're actually playing the applications, but when you're someone who's building the software yourself, you need it to run at the same speed as someone who has a PlayStation 5 at home. And what we've seen is a massive increase in the power of machines over the last 30 years. The same concepts that we had to build a game like Tomb Raider back in the 90s apply nowadays to the current generation. It's simply that we've got a lot more computing power to work with. So now we can take these concepts to the next level. But ultimately, these technologies have, these concepts have existed for tens of years that we can now apply to building a game. If we take an example of the card in this machine, which is an RTX 3090, that's got 28 billion transistors across 10,000 individual processors. So enormous amounts of work just to do something like entertainment. So how can we apply this to other domains other than games development? Well, a common use of Unreal nowadays is architectural visualization. So adding in this increase in power means that we can actually increase the quality of our graphics. And we do this using a technique that we never used to be able to do in real time. We used to have to run this on large rack machines that would take days to draw a single image. So a film like Toy Story, for example, was created in this manner. Now we can run this 60 times a second to generate it to your eyes, so we can actually move in these virtual machines. This increase in power also means that we can mix reality. So that means incorporating virtual reality headsets with holographic displays, so we can actually literally project objects into the room. And this is the wider concept of augmented reality. So augmented reality allows me to model from a camera perspective the real world environment and pretend that it's a virtual world. So I create a virtual world on top of this camera representation, and hopefully the two concepts blend together. So we'll do that as our next demonstration. Okay, so in this example, what I've got is my own Android phone, Samsung Galaxy phone, which I'm going to join in, and hopefully you're now getting a live feed from my camera. So we can see our lecture theatre environment behind us. Now, one big part of augmented reality is being able to detect parts in the real world, and we call this computer vision. So in this system, what I'm doing is measuring, looking for changes in colour, and you can see that it does a pretty decent job of being able to pick up items in the room. So really what I'm doing is building a 3D image of what's happening in reality and feeding that back into my computer to then do some work with. So we take that concept of computer vision and we use it with Unreal Engine. So what we're going to do this time is see how that augmentation works. By scanning my camera around, it can look for lines within the environment. And what we're basically doing is building a big 3D box representing our world. So on the ground here, what we have is the ability to place a plane, and on that plane, I can then incorporate virtual objects. Now, they are literally existing in this 3D world. So when I move my camera around, you can see that the objects also move with it. So I can actually stand on top of the object. Those concepts of moving the object around in the virtual world are now being handled by mobile interactions. So I can use a finger to pick the character up. I can rotate the character around, and I can use it to actually build full 3D worlds. And I can even incorporate all those physics concepts that we saw in the game application inside this augmented world. So I can actually throw objects around onto the world and drop them under physics. And you can see that the objects will scale with them. So that's the primary difference between augmented and virtual reality, but actually they're fundamentally the same concepts. And it's the job of the game engine to wrap those concepts up. So an example of this is a project that I've been working on, which is an enterprise project working with a company who make conservatories and sales applications using iPads and Android tablets to then allow us to see what a new conservatory would look like on someone's home without it being fully built. So this is the virtual reality version of that application, and we've got augmented and virtual reality versions of that application. So we've taken the data from the existing application, and what we've done is import that into Unreal to now create these real world 3D views. Now, this is a genuine VR demonstration. So that means that someone who's about to purchase the conservatory can put the headset on, see what it would look like in their garden. They can choose the different features, the different types of glass. They can actually design their object without actually it being there, doing it all in the virtual space. And that's another key feature of the Unreal Engine. As well as these architectural sides and augmented and virtual reality, another big emerging area that's being used for Unreal Engine is film and TV production. And we've got this convergence between film and television. A company called Weta Digital, who you may not have heard of the actual company, but I'm sure you might have seen some of their work. The Lord of the Rings and Hobbit trilogies were all constructed by this company owned by Peter Jackson, based in New Zealand, in their own tool set. Now, over the last couple of years, Weta have been embracing, can we do this in real time? Can we use the technologies that are used to build a game to actually build animations and film productions using this technology? We now know that this is true because Disney Plus's big hit last year, The Mandalorian, had all of its sets virtually created in Unreal Engine. So there are these giant displays on the Disney film sets, which we can see the camera arrays in this screenshot here. All of this stuff in the background is Unreal Engine. And instead of controlling it with an input controller, we simply control it with a camera crane. So as we move the camera around the set, the virtual environment moves with it. And that's what they use to actually construct the backgrounds of that. Now, to prove that this was all done in real time and in Unreal, again, what we'll do is take a look at an example of this. And the one that we'll use is that Weta Digital one. So in this example with this meerkat, the meerkat has been modeled with a recent development in games, which is how to accurately model hair, fur, and cloth. And to do that, we have this concept known as soft body physics. We're trying to represent the fact that objects are no longer solid, that they wave and move around. And we can see that we can use those techniques to build a real-time environment. So this is the environment of that scene. And you see it's a desert type scene. What we then have is the engine's inbuilt virtual production system, which is known as sequencer. Long gone are the days where games used to pre-record video. Now all the cinematics of a game are done in the engine itself. So we place virtual cameras around the world and act like we're virtual film directors to stage this system. And this example here has those built in. So we'll just have a quick look at this demonstration here. And hopefully you can see that the quality that Unreal Engine is capable of producing in real time. Notice all the puckering on the edges of the shell, the fur of the meerkat. All of this is being generated in real time at 60 frames a second. So with each scene, we're simply putting a new camera into the virtual world, moving that camera around, and now we can dynamically add in new content. And in this case, that content is an eagle. And the reason it's an eagle is simply to show off the new fur and hair rendering. So the wings, the feathers on the wings are all generated using those techniques. So a game engine, which used to be able to build a game like Tomb Raider, is now capable of generating graphics of that quality. And you can see, to prove again it's real time, those same concepts of building a level, I can also apply to this to move the grass around, to move the camera and choose where we're going to focus our scene on and allow me to act as a virtual film director. Now, a big problem that we've always had is being able to represent humans accurately. We end up with this situation known as the uncanny valley. The closer that we got to realism, the weirder it looked. And there's a classic example of a film called Polar Express. If you've not seen that Tom Hanks film, I'd encourage you to have a look at it. They accurately scanned Tom Hanks' face. So geometrically, it was absolutely perfect. If I place that virtual world like a mask over his face, it would have mapped his face perfectly, but unfortunately we couldn't accurately model the lighting correctly, and that led to this uncanny valley. Well, Unreal over the last year has been working on that to produce this concept known as metahumans. So metahumans allow us to actually model this and these facial motions. So what we have here is a character with a series of placements on the top of the face, which we can animate and move around just like we were moving those other virtual objects to actually move individual parts of the face. There is 4 or 5 years worth of research there just into how the pupils and corneas of the character interact. And hopefully we're edging towards this uncanny valley. Now, there's still a few aspects of that that don't quite look exactly photorealistic, but this is in the current version of the engine. And we're going to see improvements on this in the next couple of years, with the idea being that we can actually virtually inject actors into our world. Now, at John Moores, we've got motion capture suits and facial tracking suits that actually allow us to track our faces in real time and in effect virtually control these. So in effect, we can replace these characters and work as an actor. That just doesn't have benefits for film. That has benefits for areas like medicine. So, for example, we can do virtual consultations. If someone's anxious about seeing a particular doctor, then we can replace that with a virtual avatar. Virtual consultations is an enormous emerging field in these kind of properties outside of the entertainment industry as well. The crucial bit that I really want to get across to you is that all these technologies, all these new tools are grounded in the science of not just the last 20 or 30 years, but dating back thousands of years. So those concepts of those triangles being moved around in a virtual world are all borne out by the mathematics of people like Pythagoras. So yes, we do use a squared equals b squared plus c squared all the time to work out how a triangle is positioned. We have Euclid to be responsible for how we actually measure space and measure 3D models. We have Descartes for his ability to add in this grid, and just by constructing this simple two-dimensional grid, now we have a way of describing movement. So we could describe exactly what we mean by saying 1 unit to the right and 1 unit up. And that allowed us to represent it in algebra. If we can represent it in algebra, that means that we could represent it in computer codes. Those concepts of Descartes then allowed Newton to construct his views of physics. And if we want to drive a car in a game, or we want a football in FIFA to behave like a real world football, then we need to model those Newtonian mechanics. So things like gravity, things like being able to throw objects around, just like I showed you with both the virtual reality demo, are all driven by those physics engines. And they are just simply code representing Newton's laws of physics. Finally, we get into the computer science era. So Alan Turing and von Neumann, who are the fathers of modern computing, who defined a concept of what computation is and how a computer works, to Edgar Dijkstra, who then pioneered artificial intelligence. And that's what allows us to have virtual artificial intelligent control characters moving around in our world. And then finally, to bring this all into gaming, we then have Shigeru Miyamoto, the man who brought Mario to the world, and his concepts on game design and how we apply all of this mathematics, all of these laws, to then actually turn them into a fun, playable game where Mario can run, jump, he can squish on top of a turtle and pop its shell. It doesn't really matter that it's not a serious application for this logic. The crucial bit that is that we're applying all of those concepts to represent them. Now, on our course, we spend quite a long time focusing on Unreal Engine. So we're looking to try and build content on a yearly basis and work our students through the stages of being able to build their own full 3D games. So I'm just going to quickly show you a demonstration of a student's work from a student who graduated a year ago. I've hidden their name, but you can see that they're working for a company called Codemasters. Codemasters, one of the UK's biggest game studios. They primarily focus on racing games. So games like Race Driver Grid are developed by them. And he used his work developed at John Moores to secure that job. So this is his submission for my coursework, where I asked them to build a game application of their own choosing. He chose a squad-based tank game. So we used those Newtonian physics to model not just a tank, but also allow you to fly a plane. So he worked out the mathematics needed to steer that plane, to provide lift, and then integrate that with the physics engine, and then apply that with the graphical techniques that he's learned to then allow us to add features like this very cool radar system into the demonstration. That was 6 months' work. That was 6 months' work of his own code, but using those 7 million lines of Unreal. And without that game engine underneath it, he would not have been able to accomplish something as polished and as professional as that demonstration. So while he undoubtedly is very, very talented as a developer, he relied on the game engine to add those building blocks. The animations, the rendering, the physics was what really we were looking at. So again, I'll just show you a couple of demonstrations centered around that. Now, lots of people have a misconception that the graphics and the fact that our games look very nice nowadays comes from the quality of the 3D models and the artistic side. The artists are very, very important to building this. There's absolutely no doubt, but I can illustrate what those graphics will look like as they come out of the art tool. Okay, so you can see that they don't look like something that you'd see on a modern console. Yeah, they're very flat. What the artist has done is create the geometry. So they've used a 3D modeling tool to go and create a perfect sphere, and then they've applied a texture to it to give it that colored pattern. The actual graphics comes from modeling the physics of light. So this is called physically based rendering. To get these very, very impressive graphics and how graphics improves year on year. So why a PlayStation 5 looks better than a PlayStation 4 is that we have more power to more accurately model the physics of the light. And we can prove again that that's in real time. So I can use Unreal to drag in a new light, and you see that that light will have an effect on the object. Notice that it's also generating shadows for those objects. So the closer the light gets to the floor, you can see that those shadows start to elongate, and we can dynamically move those objects around. Each one of these is known as a concept called a material. Now, we can model lots and lots of realistic looking materials. And because we can do that, that's what allows us to extend it into areas like architectural visualization. So if a company wants to show off their building before it's built, the architect's 3D model can then be taken into Unreal, and then we can apply all these real world materials like concrete, like plastics, like natural materials like grass, all built out of these physical rules, and then use that to build up our virtual environments and combine them with these lighting techniques. The different hidden views on the game are how it then turns into a game application. So this is the view that the physics will see of the game. These spheres now have a representation which allows me to collide with them, to interact with them, to then build into actual game mechanics that we use. So I could walk up to that object, for example, and pick that object up. Now, I've mentioned that these are done in a different programming language, and that language is C++. And here's an example of some C++ code. So I'll finish just with a code example to prove how I can take this mathematical code and use it to generate a mechanic. So what I want is the ability to pick an object up in the world. So how am I going to do that? Well, as a game designer, I'll think, right, I know where I'm facing and I know what I'm looking at. So what I'm going to do is pretend I am the camera, and then wherever my hand is reaching towards, I'm going to draw a line of infinite length to see where that line intersects with the floor. So where does it pass through the floor? And what we'll do is turn on a simple line here, draw a debug line, which is going to allow me to actually visualize that interaction. So mathematically, what I'm doing is working out the starting point and end point of this line as code, and I'm using the engine's physics engine to then draw that line into the virtual world. Okay, so we'll build that line of code. This is now compiling that code. It's not a pre-made application. We're building this application live right here. So that's now built the game and linked it into Unreal. So now we've got this virtual environment, and I've got some objects that I can interact with. So we've got some cupcakes here, for example, that we can then place into our world. Now, as our character's moving about, hopefully you can see those red lines. So I've got my mathematics right. It's going from the starting position of the camera, pointing to where the camera is facing. In this case, I'm moving it about with the mouse so that when I intersect with this cupcake, the line goes through it and I can pick the object up. That, in a nutshell, is how we build games. Mathematics with 3D graphics, with the art to then build a game application. That's why Unreal is worth $29 billion, because it allows us to do all of these features. Now, these examples are using the current version of Unreal to show you where we're going. John Moore's are licensed PlayStation 5 developers, so we can actually build applications for the PlayStation 5, and they're using the new version of Unreal, Unreal Engine 5. Now, this isn't currently fully out to the public, but it will be in the next couple of months. You can download an early access version of it for free. In fact, all of these tools are actually free. Unreal makes their money from people selling what's created with them. They don't charge anything to actually start working and building with these tools. So combining all of those techniques together with very, very fast hardware, sorry, I just need to stop that older one. We can use this to build the games that you're going to be seeing in the next year or so. Now, I'm afraid it will take a couple of seconds longer. Unreal Engine 5 is very, very powerful, but even on these really powerful machines, it takes a little bit of time to work. While that's loading in the background, I'll just get to the final part of the talk. So the techniques that we use there to build that virtual world are a concept known as deferred rendering. Now, Unreal 5 has got a brand new deferred rendering system. And we can see that the individual parts of the image are used to generate our virtual world. So what Unreal Engine 5 adds is new versions of these layers to build more complex computer graphics. So it should be loaded now. And now we can build these new virtual scenes. This is a technique known as lumen. And lumen is light, using those physics of the light, but this time all calculated in real time. And that allows us to do extremely detailed graphics. We then have this second system called called nanite, which allows us to break apart the number of triangles in our level. And if we move to the wireframe mode, it basically allows us to use thousands and thousands of different triangles to represent this three-dimensional scene. So if we switch back to our game, we can live play this game, in this case on a PC, but it's the same process to get it run on a PlayStation 5 or Xbox Series X. And you can see that we can actually control Unreal Engine 5 in real time. And those same techniques, those same physics, those same translations, just using more powerful hardware and an even more millions of lines of code to allow us to use the same techniques in Unreal Engine 4 to now build the next generation of experience. And that'll be the games that you'll be playing in the next year or so. So I'm afraid that's it for my talk. I hope that's given you a good tour of the technologies that go into building a game application and all the different areas that we can now use these gaming technologies beyond just games. Virtual and augmented reality is enormously rich area that I think lots of people are going to be experiencing. We just need to get to the point where we can have these augmented devices out in the public a bit more. So things like virtual glasses, areas that we're currently researching in order to use these techniques. But what is clear is that they're going to be powered by this $29 billion game engine. Okay. Before I finish, has anyone got any questions they'd like to ask me in the chat about what I've covered there? Anything that they want me to clarify? If you can, post the messages in the chat or in the QA. No, okay. In that case, thanks very much for listening to my talk. We'll take a break for a few minutes before we move on to our next speaker. Thank you very much.